Okay, thanks everyone for coming today to David Green's talk. He'll be telling us about this nice subject, which I'm very excited to learn a lot about, which is somewhat higher Tannaka-Krein reconstruction. And yeah, for a novice like me, I'm excited to hear what that's all about. So whenever you're ready, take it away.
Okay. Just quick show of hands. You could use like the Zoom thing. Who knows what a bialgebra is? Okay, cool. So I'm going to sort of skip some of the basics and move a little bit fast, but I promise I will. If you've never seen this subject before, we will get like a somewhat hands-on about three-quarters or half or three-quarters of the way through. Also, if you've ever given a talk at OSU, I know Hank has, we have tradition here of just interrupting the speaker constantly. So feel free to just ask questions. I actually have a kind of limited time afterwards to stay. So ask during the talk. Okay. So today we're going to try and, review just like the basic notions. We'll talk about the history of Reconstruction just as a thing. We'll have an ice cream break. The ice cream is very important. And then we'll kind of get into a proof. And I'm going to mostly talk about bialgebras today and not Hopf algebras. So the thing with Hopf algebras is it's a bialgebra with an antipode, which satisfies some properties. And that antipode is unique if it exists. It corresponds to duals on the tensor category side, which are also unique. They exist. So there's just some computations you have to do to prove these things exist, and I kind of don't want to get into it. I think the bialgebra story is much more interesting. Okay, so we're going to be living in some sort of ambient monoidal category up here, right? And we know that an algebra has a multiplication and a unit, which has to satisfy a unitality triangle and an associativity pentagon, right? If you're an algebra in a general monoidal category. Coalgebra is the same thing. You just flip the arrows. And it has a co-unitality triangle and an associativity pentagon, or co-associativity pentagon. Let's fix that. So there's a co-unitality triangle and a co-associativity pentagon. But really, you just flip all of the arrows, and you're good to go. Now, this is pretty easy to check this lemma with the star here. That a bialgebra is equivalently a coalgebra in the category of algebras and algebra homomorphisms, or it's an algebra in the category of coalgebras and coalgebra homomorphisms. For those in the know, these things can only be defined in monoidal categories. And so for this to make sense, you need a braiding in your ambient category. So I've boosted us to some braided monoidal category C. That means the category of algebras is monoidal, and both of these categories down here actually make sense because you need to have a monoidal category. Okay, and I guess also for people who like this perspective, this is an instance of the symmetry of the Boardman-Voigt tensor product. You do not need all of that machinery to prove this. You can just write down the four squares you need to commute and check that they're the same, but that perspective will become useful later. And then the reason that we have bialgebras in the first place is so that the representations are a monoidal category. And if you're semi-simple, basically by definition, that monoidal category will also be semi-simple.
So I missed the point. Where do you need a braiding?
Sure. So if algebras only make sense in a monoidal category, right? Okay. So the tensor products here, I'll just show it, right? So if I have something like A is an algebra and B is an algebra, I tensor them. So I have another copy of A and B here. And now I want to multiply, right? I have to braid the A and the B together so that I can multiply them to get A and B. Right, and this ends up being just like super important. So that's the tensor product of algebras, but it only works in a braided category. If they're commutative, then there's like something else that you can do. But in general, you need a braided category. right? Or you can't even define commutative without a braided category. Okay, so sort of a question. If I give you the equivalence class of modules for an algebra, just as a category, it's equivalence class, can you get the algebra back? Anyone want to venture a guess? If you already know, let others think about it for a minute. Okay, and the answer is kind of famously no. This is actually a super nice thing that the answer is no. This is called Morito equivalence. And in a lot of contexts, it's going to allow you to replace some sort of nasty algebra with an easier one that you can think about instead. The first example is I guess I should use mod and not rep. Okay. Modules for C, that's isomorphic to the category of vector space. Oh, sorry, wrong C. Modules for the complex numbers is the category of vector spaces. And let's just say all of my modules are like finite in some sense. So I'm doing finite dimensional vector spaces. That's the same as modules for MNC. So this is what it means to be Morito equivalent, and there you go. Okay, so we can't get our algebra back this way, but maybe we could do something else. And so here's a formalization of the problem. So I give you some category, maybe it's a fusion category, maybe it's semisimple monoidal, maybe it's semisimple, right? I can add a lot of adjectives to this. I could add braided, symmetric, etc. And some sort of nice functor, which at a minimum will be faithful. If the domain has a monoidal structure, I'm going to want that functor to be monoidal to the category of vector spaces. Can you find some sort of algebraic object such that the category you started with is equivalent to the category of modules for the algebraic object? So that could be Hopf algebra, pi algebra, just a regular algebra. But I don't just want it to be abstractly equivalent. I want it to make a commuting square with my functor f. Right. I want it to sort of be isomorphic to the functor f.
So how does this interplay with the Deligne theorem about tensor categories?
So Deligne's theorem on tensor categories says that if you have a symmetric monoidal category, which satisfies some other condition about being more or less small enough, it has a symmetric monoidal fiber functor to the category of supervector spaces. So I will talk about that a little bit more in the history slide. Right, it won't quite go to vect, which is the version that I'm going to do today is the easiest version where everything goes into the category of vector spaces. I'll talk about super vector spaces just for a little bit.
Well, but Deligne theorem, I mean, in the old-fashioned formulation, it does mention some supergroup.
Yes. So Deligne's theorem, right? Deligne's theorem, yeah, it'll come out of this, right? But it'll come out of a slightly more complicated version of this theorem where this thing here, sorry, I'll put that in red, where this guy doesn't have to be vector spaces, it can be super vector spaces.
No, that's right. But you just say that you just stated the Deligne theorem as the existence of a functor to super vector spaces, but where is the group or supergroup?
And from that you can take a look at what a Hopf algebra and super vector spaces looks like. That gives you a symmetric monoidal thing, and that will produce your supergroup for you.
Right. All right.
Right. Yes. Yeah. Deligne's theorem reconstructs an affine group scheme, blah, blah, blah. But when you look at what it actually turns out to be in vector spaces, you get a supergroup. Sorry, in super vector spaces, you get a supergroup. Right. So
David,
yes?
I had a question. So this question that you're wondering about, like if you have the category of equivalence classes of modules of an algebra, and you want to say if you can reconstruct A, is this like a purely math question, or is there like some physical significance to why we we consider this question?
I will defer that question for about a minute and talk about the history of this sort of thing, which is
Okay.
mostly but not entirely pure math. And then
Okay.
you can interrupt me again.
Sounds good.
Okay. So I was about to say a lot of these, so let me circle, right? So these, I believe, are physicists that had a reason to care about this. So the first idea of doing this was kind of way more analytic than anything we're going to do today. They were thinking about reconstructing a, given the category of representations of a locally compact topological group and the fiber functor to vector spaces, but this time not finite dimensional, can you get the group back? And Tannaka and Krein did like the two directions of this, one where you get the category and one where you get the group. And then Ravano sort of just algebraicized the problem and got rid of a lot of the topological things, and was the first one to sort of do Tannaka-Krein reconstruction on the algebraic side. Unfortunately, there was a hole in the proof, which Deligne fixed in 90, which is why he gets a large amount of the credit. But this work by Ravano in 72 is actually very insightful. There's a lot of cool things in there. Okay, and then people put the analysis back. So there were sort of reading left to right here. There were some things about locally compact quantum groups. Doppler-Roberts had a theorem that was sort of more in the initial Tannaka-Krein style. Majid thought about rational conformal field, the relation between this theorem and rational conformal field theories. This paper of Schonenberg in 92 started to remove the semi-simplicity assumptions. We are not going to be doing that, but I have it circled in purple because the approach was really good. And if I had read this paper before trying to write my own, I would have saved like 6 months of effort. So that was my thing to read all of the, really read the bibliography in the tensor categories book. And then some more algebraic generalizations. Day in 96, and this paper of Lentner and Lombelli from yesterday on the archive, they start handling things when the case where the fiber functor does not go into the category of vector spaces. Deligne, of course, in 90 considered super vector spaces, so it was either vector or super vect. But then, Day and this recent paper, the where the fiber functor lands can just kind of be arbitrary. Nice, but arbitrary.
But Doppler and Roberts, aren't they algebraic quantum field theory people?
I am a pure mathematician, so that is physics to me. You may have a different opinion.
No, just asking. Like, okay. what did they do? What did they study?
Yeah, I think AQFT is right. I mostly just read this paper for a couple of insights. I'm not really familiar with their wider work, but I know that there's some things in there.
I bet some von Neumann algebras.
Yeah.
Okay.
I will say that so if you want to, so here's a reason to care, although I am still looking for reasons to care. If you are comparing like Kitaev models versus like Levin-Wen, the two ways that those models are described sort of have this reconstruction theorem. It's implicit when you're comparing them. I don't think physicists have a reason to maybe write it down into the same level of precision, because why would you? But when you compare those types of models, this idea is implicitly there because the original description by Kitaev was in terms of Hopf algebras, and the one by Levin and Wen was in terms of like a category. Okay, Hank is going to correct me on the physics here, I think. Yeah, just interrupt.
Yeah, so I think the connection with so this is really more about the difference between Hopf algebra and quantum groups. So in terms of quantum groups, which shows up in, for example, Chern-Simons theory, and even just more general algebraic quantum field theories, for example, these things are, they kind of carry functional data in some sense, or functional properties, in addition to the algebraic properties, which is like the Hopf algebra side of the story. So quantum groups themselves, you take functions on the Lie group, and then what you have to do is you deform it, and then you do a whole bunch of norm completions. Like that's what you have to do to get an actual quantum group. And that is the thing that shows up in QFTs. And it's kind of a cool thing that in just TQFTs, for example, just topological theories, like all you need to care about really are like the Hopf algebra piece inside of your quantum group. So for the Kitaev model, for example, like it's mostly made out of like Drinfeld double or something like that, and stuff is well, of course, if you have finite groups, then there's no functional analysis to speak about, but nevertheless, you can still just kind of see that in TQFTs. It's mainly the Hopf algebra that's kind of play a significant role. But when you get to like more complicated QFTs or CFTs even, then the actual functional analytic properties, like, whether you like the stuff that you would miss otherwise if you don't do any completion, normal completion, which is something that you need to do in order to get a monoid algebra. For example, if you do like the GNS construction for these quantum groups, then you will miss like gap pieces.
For Van Neumann, I don't do norm completion, I do weak completion. But all right, so I don't know if everybody lost as me, but let me just say there is a motivation, I guess, from 2D quantum field theories. So this category of modules is the category of boundary conditions, and you're just asking what is the bulk theory they are coming from. I think this is a pretty clear motivation for Tannaka-Krein motivation.
That's great. That's very helpful.
I don't think it's preconditions, right? You're asking about boundary conditions. Like the modules describe the operator algebra itself.
Well, I mean, isn't that the point that they do both? Let me get a little bit further, and then we can probably circle back to this. Because I do want to start talking about the categorified story, right? Because eventually we want to start doing 3+1D stuff. Hopefully I don't need to motivate that so well, right? Like just go up in dimension. But there you write everything down, and you really realize you're starting to work with two categories in somewhere in the story. And this was first conjectured to work the reconstruction story all the way back in 95. But and then there's an article in 2007 that sort of did the tri-algebra perspective of this. And then two articles recently, one that did the sort of the version that Roman was thinking about mentioning earlier, where you actually get a group back, right? So they're reconstructing a supergroup in this. And then, recently I was able to kind of extend that a little bit to the Hopf algebra case. In order to make this really imply this, you need to have a version of the, it's got 4 names on it, the constant Gabriel-Carter theorem, and I missed one. That tells you that if you have a Hopf algebra and you take its group of group likes, and then you take the group algebra of the group of group likes, you get your Hopf algebra back. You sort of would need that result to make this my work strictly generalize this, and I don't think anybody either knows how or wants to prove that right now. So as it stands, these are kind of incomparable. They do different things. Okay, so I want to kind of circle back to 1 categories. And I did promise in the abstract for this that I was going to give like a decent proof for people who had never seen this before. And so if you have seen this before, hopefully you haven't seen this proof style unless you're Hank. But the goal is really what I'm going to do is I'm going to provide a really good proof for 1 categories. And then I'm going to say, okay, you replace 1 with 2 and 2 with 3, and you now have a correct proof for 2 categories. The only other thing you have to do is update your references file to actually like point to the theorems that you say you're using, right? like that's the style of proof that we're going. Okay, so in order to do that, I want to formalize the problem a little bit more. So if you have a semi-simple category and a functor to vector spaces, it sort of naturally lives in this 2 category, and I have that in quotes for a reason that we'll see soon. 2 vect over vect star. So this is a slice category. What are its objects and morphisms? Okay, so there's objects that look like a functor from some category C you don't know. The vector spaces. It's a linear functor, and the category has to be semisimple, finite semisimple. A 1 morphism is a commuting triangle like this one, with a specified sort of way of commuting. There's a natural isomorphism tau in there. And I'm going to call this an ice cream cone, and we'll see why. And yeah, the important part about f here is that f must be faithful. I want f to kind of look like a forgetful functor, and so I need f to be faithful, and that's super important. Okay, and then 2 morphisms look like eating ice cream. You put some ice cream on your cone, and then you eat it. So it looks like sigma from t to t prime, you know, just like some extra data. So the data of the actual 2 morphism is just this sigma. Okay. And then in order to compose things in this category, you just stick the diagrams together. There's generally only one way to do that, and you know it works. It's actually a 2 category. 2 category in quotes because this is really a 1 category. What do I mean by that? Oh, and also this is what we do here is we eat ice cream. This is how we prove things. Okay, so this category is 1 truncated. What does that mean? It means that between any 2 1 morphisms, there is at most 1 2 morphism, and if it exists, it is an isomorphism. So it looks like I took a 1 category and I just stuck some identities on there. It's equivalent to 1 of that form. Okay, so here's the proof. Just take the thing that says there's a 2 morphism between, figure out what this says here. That's the same as this equation. Tau and tau prime are both isomorphisms. So that tells you that f prime of sigma is an isomorphism. And there's a formula for it in terms of the taus. So it's definitely, and then f prime is faithful. That's the important part. So it reflects isomorphisms, and because it's faithful, it's like injective, right? It means it's injective on morphisms. So sigma is unique if it exists. And since f prime reflects isomorphisms, sigma must be pointwise and iso. And the fact that it's reflecting isomorphisms here, meaning that if f prime of sigma is an isomorphism, sigma is, that's right. I'm using that. I'm in like a sort of nice category, right? Semi-simple is overkill, but like definitely abelian or something like that. So I know that monic and epic actually implies an isomorphism. Okay, so I have a 2 category that looks like a 1 category. So you know, now the following sort of problem makes sense, right? So here's a reconstruction problem. You have a contravariant functor from the category of algebras, let's just say inside vector spaces, to which assigns an algebra to its category of modules together with forgetful functor. Right, that's a functor from something that looks like a 1 category to something that looks like to a, let's say, a truncated 2 category, so everything checks out. If this bothers you, just throw some identities on the category of algebras to make it a 2 category. And we want to invert this functor, right? You know, that subsumes the sort of the statement of reconstructing a category of an algebra from its category of modules.
So what's the right way to think of this forgetful functor, or whatever, the functor to the vector spaces?
Great question. I am glad you asked, because I wasn't going to do this, and now I am going to do this. Okay, so, oh, okay, yeah. I was going to do my Billy Mays impression, but we'll do that in a bit. Sorry, my thing is not scrolling. Give me a second. Hello? Okay, whatever. Okay, yeah, my GoodNotes just locked up. That should close it. There we go. Okay. Sorry, I'm gonna have to scroll. I know everybody hates. Oh, great. No, I won't. Okay, so what is the correct way to think about the fiber functor? Do you know the what's the name of this theorem? The theorem that says that every finite dimensional semi-simple algebra looks like a direct sum of matrix algebras.
Yes, I know the Wedderburn theorem.
Okay. Every finite semi-simple category looks like a bunch of like basically a direct sum. I mean, it literally is of vec to the n. So just a bunch of copies of vector spaces, direct sum together. So my claim is, if you like unwind about functors preserving direct sums and blah blah blah, is that it given a category that looks like vect and some functor from vect to itself, it suffices to figure out which mn this vect came from based on f. So this is going to be equal to modules for MNC. And our goal is to recover n from this situation. This is enough to, it's kind of not the greatest proof because it doesn't categorify well and it doesn't tell you as much as it could, but this will give you a statement which implies, say, algebra reconstruction.
So what's the analog of the Wedderburn theorem for categories?
No. It's not the analog of the Wedderburn theorem. It's the analog of the theorem that says a vector space is determined by the rank of its basis. Right? It says that finite dimensional semi-simple categories deserve the name two vector spaces because they have a rank. They all looked like, vect to, okay, there's some operation which I'm not going to tell you, and right, just like, or what's my just like arrow? Just like every single, so I guess this is equivalent to C, right? Just like every vector space.
I feel like I'm missing a lot. Like you're talking about tensor categories like linear over C. I don't know.
No. I'm just talking about a finite. So no monoidal structure. It's just a bunch of objects that you can like direct sum and things like that. The monoidal structure will come later, and that's how we'll get the Hopf algebra structure back. But you asked what the role of the fiber functor was, and so I'm just doing algebra reconstruction right now. So given something which is categories of modules for an algebra, figure out which algebra it came from. How does the fiber functor do that? Well, inside here, there's a distinguished object, which looks like the complex numbers, right? It's the generator for this category. Everything else is a direct sum of this one object, right? So f of the complex numbers looks like something. Actually, I should do c to the n. And then the point is that and f is isomorphic to MNC.
So you sort of enlarged your vector space when you're doing this. Like it's kind of like you're taking some. Yeah, go on.
So this is maybe misleading, right? You have the way that I've written this. You have some category C up here. Sorry, there's too many C's floating around. So some category C up here.
Okay, so is it correct to say that you sort of fixing the algebra in the Morita equivalence class using this functor?
Yes. Okay, that is exactly correct.
Yeah, I don't feel like it, but I think I'll eat it until the end of the talk. And
I mean, the functor literally does fix the algebra in the Morita equivalence class. And the point about the classification theorems tell you for these things that it suffices to do that for the Morita equivalence class of the complex numbers, and then you do some abstract nonsense and it tells you everything else.
Yeah,
that's precisely what it does. Okay, I wanted to say, but wait, there's more here, because this problem we can add some adjectives to this problem in a way that's useful.
David, before you move on, can I ask an extremely basic question, which will bother me for the rest of the talk if I don't ask? If you scroll up a little bit to the ice cream cone.
Come on, please scroll. There we go. Okay, what's up?
So for a two category, you have some objects, and the objects here are C to vect, some functor which is given by C to vect, right? some morphisms, one morphisms, which are morphisms between these functors,
Mhm.
and then two morphisms, which should be morphisms between these morphisms. I am just having trouble seeing how that is given T to T prime.
Two morphism. I mean, so I'm sort of declaring it, but I'm declaring that these are what the two morphisms look like. The two morphisms look like some sigma. It's just a natural transformation, right? Between so a two more.
Right, it's a natural transformation, and so it should right. So it's just a morphism between the categories.
Between T and T prime. So like my two morphism. So here's my first one morphism. Here's my second one, right? And then my morphism is just my two morphism is just wrong color. Is just this guy.
Very good. Okay, thank you so much.
Right, and then you can see that I can compose them vertically by like stacking them. Right, if I had another like sigma prime between T and T double prime, I could just like stick it on top, and then they decompose.
Lovely. Thank you so much.
Okay. This is important because we're going to talk about the slice category more. It's actually symmetric monoidal. I can use the fact that vect is braided again, right, to tensor categories with the Deligne tensor product here. And I'll get something, a nice tensor product that looks like this. You just stick the functors next to each other and then use the fact that vect has its own tensor product to actually get something that goes back into the category of vector spaces again. And the unit is just the identity on vect. So that's great. How do I get an associator, a pentagon, etc.? I'm just going to use the one that I already have from the category of vector spaces. Okay. And then for the symmetric structure, guess what? I'm just going to use the one that's already there on the category of vector spaces. So right, to swap two functors, I'll just take the regular tensor product, do the swap on vector spaces, and then take the tensor product again. Right? Very, very, very boring, hopefully. Okay, but now that I have symmetric monoidal structures on both sides, I can try and find a symmetric monoidal equivalence. And this will actually tell me a little bit more than I know I have a symmetric monoidal equivalence. So this is the problem here that we are going to solve. We're going to invert this as a symmetric monoidal equivalence. Okay, how do I do that? As we saw earlier, I want to fix the Morita equivalence class of the algebra, but I don't want to make any choices doing it. I want to do it in a natural way, so I can leverage that. So I'm just going to send a functor to its endomorphisms, and then given a one morphism like this, I'm going to send it to conjugation by tau. So what does that look like? It's kind of annoying, but if you have something that lives in the endomorphisms of this functor, then I can sort of I can write down this formula. So to get something in the endomorphisms of this functor, and remember that it was contravariant. So this is what we wanted. We want to go the other way, right? And it's just conjugation. You sort of go over and you use all the data you have exactly once. And conjugation is obviously an algebra homomorphism, which is good. Before somebody correctly points out that I didn't tell you what to do with the two morphisms, well, they have to go to identities. That's the only place I could send them. But then you have to check that it's actually a functor. Right? That's non-trivial work, checking that the assignment that sends every two morphism to an identity actually gives you a well-defined functor. But it does. Okay, and then this conjugation formula is a nice algebra map. Okay, so why is this an equivalence? The first one, and I was gonna spend some time here. Good, it looks like I still have it. Okay, so what do I do? What is my unit and co-unit to actually witness that this is an equivalence? So I need to find a map which is an isomorphism from A to end F. How do I do that? So I have a little a and A, and then let's say I need a map from f of C to f of c. Well, well, this is the forgetful functor from mod A. Oh, sorry, this is, let me fix that. It's the endomorphisms of forgetting A. That's important. So whatever f of c was, I mean, it's the underlying vector space of an A representation, right? So I can just take rho c of A. Why is that natural? Well, it commutes with, well, intertwiners were the things that commute with this action. So the action commutes with the intertwiners, right? This is a natural transformation by just like flip-flopping which things are commuting with. Okay, so that's the map, right? On every representation that you forgot, we're going to do the action of A. That's natural. Why is it an isomorphism? The answer is because basically the innate element, right? You have to take a colimit completion in there, blah, 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 abstract nonsense, but the real answer is the innate element. For those of you who maybe know some operator algebras about double commutants, right? That is, in my opinion, the correct intuition, right? The things that commute with the action is just the action again.
Well.
Okay, that's the intuition for how to think of it. These don't live in the same vector space, so you can't just get away with literally saying that. But it's a pretty straightforward thing to check just abstractly. The other,
I mean, it's rather confusing because again, like if so this property distinguishes von Neumann algebras, right? I mean, like here it's not, well, like categorically, von Neumann algebras are like Banach spaces with pre-dual, but I have no idea how to relate it to this.
It's intuition that I will go into if we have time. I sort of, if you, I don't know, so my advisor is a von Neumann algebraist. So I tend to think about category theory as functional analytically as possible. Sometimes this is an example of that. What I said was not a precise statement. I'm happy to move on because I have just enough time to cover the things that I want to cover. Okay, so this is the idea of how to invert this. Again, you do need to like use the innate lemma, blah, 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 to actually get this. This one is much more interesting. Okay. So I have a category and some functor, and I want to know, and I need an equivalence of categories to modules for the endomorphisms of that functor. Okay. Now, the great news is that every object in the image of the functor canonically has an end f action. That's the point of the endomorphisms of the functor, right? It just acts pointwise. And so I can just send C to f of C with its natural end f action, and that gives me a map to end f modules. The question is, why is that an equivalence? Okay, so
I think that was too fast for me. Can you sort of say that again?
Sure. So so how does end f act on f of C? Well, I'm just going to take the leg at C, right? So if I have eta in end f, right, that comes with, by definition, that comes with a to C from f of C to f of C.
Cool.
So this algebra acts on every f of C in a way that's compatible with composition because the multiplication on both sides is just composition. So every pointwise. So every object in the image of f just has this action of end f floating around, and so I can upgrade my functor to sort of go to modules for the endomorphisms of f.
Makes sense.
Yeah, just for free. It's just hanging around. Okay, but what's not, so this is like clearly faithful because it's like identity. Sorry, it's clearly faithful because f was faithful. What's less obvious is why this is an essentially surjective functor, and to prove that, we're going to handle this as abstractly as possible. Okay. Remember that there's no monoidal structures or anything right now. We're going to get that in just a minute. But what am I going to do? I have C. There's a commuting square here, and this is where I'm using semi-simplicity in a massive way. If you are not semi-simple, not finite, you have to do a bunch of stuff with coalgebras, and this step will not work. I believe. Well, I mean, I know for one category there's a way you can get around it. I believe the same is true for two categories, but that is a belief. Okay, so here's C. Here's vect. Down here is modules for some algebra. This is just some algebra. I have no idea which algebra this is at all. This is an equivalence. This is F. This is the complex numbers. And over here, I'm just going to tensor with some module. I have some bimodule. Let's just say that. So A, M, C. Right? Some bimodule M. The fact that everything can be written this way, or if more abstractly, that the Morita map is an equivalence, is basically the definition of how semi-simple things work. Okay, so I have some bimodule. So here's my bimodule. Okay, and I can upgrade this bimodule. Upgrade to an A, M, and M, A bimodule. Right.
So this, I guess you need an invertible bimodular, right?
No.
No, not necessarily.
Not necessarily. It'll be invertible.
I see. I'm just yeah. I was just wondering, like, maybe this is where you need like a dual to A. Like you can see that, like, for example, this module is more or less like a dual, right? Dual yes. A.
This is the dual. This is the dual module to M, or well, it will be in a minute. So, right, and now we just need to know for abstract reasons that this. So, by the way, this where I just upgrade the action here corresponds exactly to upgrading here. Right, I just recognize that the endomorphisms just act on the right. And so we just need to know that this is a Morita equivalence. And it is. That's the point. So you can just prove a theorem about semi-simple algebras that says that if M is faithful, which it is because it came from a faithful functor, then this bimodule just is a Morita equivalence. Right. So then we know that C, that's equivalent to mod A. That's equivalent to modules for end sub M. Oh, sorry, that should be n sub A of M. I just freaked out. N sub A of M. And since the Morita map, which assigns functors to modules and vice versa, is an equivalence, the endomorphisms, I just did it again. The endomorphisms of the module are the same as the endomorphisms of the functor that it was designed to replace, because that's what equivalences of categories do, right? And this composite equivalence here is, okay, if you want to be technical, naturally isomorphic to the one that I wrote down up here. Okay. So now we know that this end construction is an equivalence of categories. Okay, what do I get from it being an equivalence of categories? Oh, by the way, it's not just an equivalence of categories. I'm not going into it because I don't want to, but it's symmetric monoidal. You just check. That also uses semi-simplicity because at some point you have to know that you need to know this. So F, let's just say box times G, that's isomorphic to end F tensor and G. That's what it means for this to be monoidal. Obviously, if this is monoidal, it's going to be symmetric monoidal, like just flip everything. Why do you know this? For semi-simple things, it's easy. You can get away with it in slightly higher generality. But again, the fact that this is like manifestly monoidal is really leveraging semi-simplicity. Which is, again, not necessary. But if you want to work with non-semi-simple things, you have to do some kind of complicated co-limits, and it's currently unclear how to do those co-limits in two categories, at least to me. Okay. So if I have a symmetric monoidal equivalence between two monoidal categories, their categories of monoids are also symmetric monoidal equivalent. The category of algebras. Sorry, I use them interchangeably. Okay. And here's a proposition which you can just check directly. And I think we will have just enough time to do that. I'll circle back to it. Which is, the proposition is not literally due today in the 70s. It's like slightly different, but you use the same proof. That if you have a monoid in this category, it corresponds to a monoidal functor. Okay, and we're gonna see one half of that correspondence in a minute. Okay, so remember that this equivalence was contravariant. So from a monoid in the slice category, I get a comonoid in the category of algebras or a bialgebra. And this is the statement that we were after. Really at the beginning, right? If I start with a category of modules and a monoid structure, meaning the tensor structure on the forgetful functor, then I get back my bialgebra. And then at this point, if you wanted to do Hopf algebra things, you would just check that the induced structure from the dual, because remember I have a functor, the induced structure from the dual corresponds to an antipode on the Hopf algebra. That is not quite as easy as I made it sound. It's like the annoying computation, but you can do it. And you just have to check that it exists and not that it satisfies any property about going back and forth, because they're unique. Okay, we are going to return to this proposition for the last 5 minutes of the talk, I think. But for right now, I want to talk about 2 categories, 3 categories, maybe some 4 categories, I don't know, and some other things. Okay. Here's the definition of an algebra in a 2 category, just if you hadn't seen it. And the idea is it's a monoidal category internal to something else. So it has its own multiplication and pentagonator, and it's got some unitality and stuff. And if you want a coalgebra, flip the arrows. Just like before, so I should say, by the way, I'm going to very briefly do the story for 2 categories, which is original to me. And just show you how it's done. But the answer is it's done the same way, right? You check out what an algebra is and a coalgebra and your Boardman-Voigt tensor product symmetry, or you can do it directly. It just takes like 15 commutative diagrams this time, that a bialgebra can be equivalently defined as either an algebra and coalgebras or a coalgebra and algebras. Okay. And we want to redo the reconstruction story this time. And then the important part here is that, yeah, representations of a bialgebra, still a monoidal category. So what do? You start with 3-vec, so the 3 category of finite semi-simple 2 categories, with functors into 2-vec. You look at the things which are faithful at the top level. That's what the star means. So they're injective on 2 morphisms for the exact same reason as before, where you have an equation and things reflect isomorphisms. This is a 2 category. So it makes sense to say that the endomorphisms construction will invert the map that sends and this now it's a monoidal category object to its 2 category of modules together with forgetful functor. And this is a symmetric monoidal equivalence. Okay, And then so now I have a symmetric monoidal equivalence between the categories of monoids. The last thing to check is that, oh, well, monoidal functors actually correspond to monoids, and you just check that they do. So, and we're going to see how this works out in a minute with the ice cream. But before we do that, where are we going with this in the future? The idea is that we are not using the full power of the symmetric monoidal equivalence, because not only does it tell you about regular monoids, it also tells you about monoids at different levels of commutativity, right? It tells you about commutative monoids. This category of commutative monoids are equivalent. It tells you that braided monoids are equivalent. And that should tell you the quasi-triangular versions of this theorem, which is like not quite trivial, but close to trivial to deduce for one categories from what we've done today, and equally difficult for two categories from what we've done today. So I'd like to do that. I'd like to write down some maybe not very interesting 3D lattice models. I say they're maybe not very interesting because the collections of two categories that actually admit nice functors the way that we're describing is known to be very small. It is what it is. In my bragging on my own work here, I think the proof is in the pudding, right? If you told me how to write down a monoidal 3 category, I could maybe push this through one level higher and I wouldn't expect anything to change. Okay, so maybe we write down some lattice models that suck. The thing that we could do, which is maybe more interesting, is assume that this is true one level up, right? Write down what it means to be a monoidal 2 category object and their co-monoidal 2 category object. And then try to write down some fusion 3 categories, right? In terms of, or fusion 3 categories that have a fiber functor in terms of their underlying Hopf algebra. And then if somebody's really, really good at physics, which I am not, you could try and write down something, 4 plus 1? Am I counting right? I think 4 plus 1. And those might be more interesting. The fusion 3 categories that you get from a monoidal, a compatibly, like a Hopf 2 category. Those might be more interesting. So I have one computation I want to do just so that we see it, and then I have a few minutes for questions. Thank you for everyone for being polite and holding them. I really appreciate it. I can say everything I want to. Okay, so we're going to eat some ice cream now for the last couple of minutes. Okay, so from a monoidal functor, I need to produce a monoid in the slice category. How am I going to do that? This is the proof that monoids correspond to monoidal functors. Well, here, okay. Here's my random category I don't know anything about, except for the fact that it's monoidal, so it has a tensor product. Here is, I'm going to do tensor last, and then I'm going to do the tensor on vector spaces. And then I'm going to do f box times f. That is the tensor product in this category of the functor with itself. For this to be a one morphism, I need something that fills that. Thankfully, monoidal functors have tensorators, so that's what can go there. And then for my unit, I'm just going to take the identity on vect with itself. There's a unit map to C because it's monoidal. And then that commutes with the forgetful functor if you use the uniter for f. Okay. And in order to check this is a monoid, I get, let's see, a bunch of stuff here. So here's the short composite. C, right? And then there's a lot of stuff down here, which I'm not going to talk about, right? Just to write it down. But I mean, you can tell what it is just from the functors on the top. Okay, and then there's the long composite, which looks like this. Oh, sorry, I missed a parenthesis somewhere. Content outside of the page. We will be ignoring that. Okay. And then there's a long composite, which looks like swap parentheses. How do I swap parentheses? Not like that. Do the other tensor product. Tensor again. Oh, and then tensor again. Okay. Question for the audience. So I've set up my ice cream cone. What goes in the middle? What's the ice cream? It's a natural transformation that C should have between associating one way in tensoring and associating the other way in tensoring. It's actually the associator on C. So this is where I use the associator on C. When you do this proof one level up, everything works out, and you use the pentagonator in the exact same spot to do the exact same thing. So I didn't tell you what the actual cone was for this functor, but again, it's actually, you can deduce it from the functors on the arrows, right? Or what the monoid axiom is. So that's everything I wanted to say for today. Thank you very much for listening and for all of your questions. If you have more, I'd love to take them.
Thank you so much.
Thank you. Are there any further questions for our speaker?
Yeah, thanks for the talk. Well, can we see the original Tannaka-Krein Reconstruction statement again?
Oh, okay.
I think the most basic one, or for one categories.
For one categories. Maybe. I mean, maybe. Oh, sorry. Wow, there's more things here than I thought there were. Maybe did you want this?
Yeah, right. Okay, so this is the statement, right? So fusion, semisimple, monoidal. So all right, so is it like, so okay, we want to recognize in some abstract category a category of modules, right? And modulus for some so you're saying it's going to be by algebra, right?
Right. If the category that you're trying to recognize is monoidal, then it's a bialgebra.
Right. And so okay, so in the existence of the fiber functor, how like, okay, when I understood its role, but is it like a rare condition to satisfy, or?
Let's see. So for two categories, yes. For one categories, less so. This is surprising to me. It may be surprising to that it's rare. I need to understand some homotopy theory about why. For one categories, there exists some things that have fiber functors that basically are not built from a finite group. For two categories, that is not the case.
So say again. So if something is built from a finite group, there exists a fiber functor, or it does not exist.
If built from a finite group means you have you're taking representations of some group type thing, yeah. Right? Yeah. There for one categories, there are loads of examples of things that admit a fiber functor where the underlying Hopf algebra that you can reconstruct, or bialgebra if you like, is not group-like. It's in some sense not built from a finite group and some cohomology. There's a precise definition of that, but I'm going to elide that for now. So there are, for one categories, there are lots of examples that are kind of exotic in some sense. And for two categories, there are not. And For 3 categories, it is not immediately excluded by the homotopy theory, but no one knows how to deal with that yet.
Wait. So again, so for one category, so
For one categories, it is not. It is a property. It is somewhat rare, but there are lots of examples.
And what's not an example? What's
the Fibonacci category will not have a fiber functor.
Okay, good. Yeah, thank you.
Right. To circle back to Deligne's theorem, if you're willing to do things slightly more abstractly, you can get rid of this vector at the bottom and work with super vector spaces instead. And then Deligne's theorem tells you that if you're symmetric, you have a fiber functor to super vector spaces, and then you can recover an affine group scheme, which again just turns out to be a group together with a element, or the the group algebra of a group together with a central element from that functor. And the central element right there of order 2 is producing the grading to tell you, like, the 2 cosets of it are producing the grading on the representation, if that makes sense.
And so for, say, okay, if I want to study modulus over some von Neumann algebra, so there are too many modulus, right? So it doesn't fit into this
TBD. So one thing about if you want to talk analysis, I love to talk analysis. One thing about that's not true at all. One thing about this map here, where did I put it? Sorry. Okay, so one advantage of the approach is that it kind of separates the analysis and the algebra, because I can have just a regular 2 category where all the objects and morphisms and whatnot have to satisfy some analytic constraints. But if you think about, is it true for von Neumann algebras? I don't know. Okay, if you think about C-star algebras, right, all of their homomorphisms are automatically contractive.
Right.
And so I can put a norm on the endomorphisms that just is the soup of like all the legs. And then this map that I've written down here is actually a norm 1 map. And for the same abstract nonsense reasons, it's actually an isomorphism. And that part fits perfectly into this formalism, because it didn't matter what the actual, right? I just had a category, and it could have been bigger or smaller or whatever. Like the slice, like how big the slice category was didn't really come into the story. This part where you have to do some stuff with modules and Morita equivalents is much trickier, and I believe it works. And my friend Gio and I, we need to read the references to this, and then we think we can extend this too. But you kind of have to know what a C-star, like you have to do C-star higher category stuff, which I am not very good at, but I know people who are.
Right. David, I also have a question about this part. So in particular, this inverse functor that you written down here, for at least for quantum groups, right? At least for quantum groups where I'm not just thinking about the underlying Hopf algebra of it. I want to actually look at the possibly non-finite, non-semisimple modules of this quantum group. And down there, like if you scroll down a little bit, we wrote a formula, maybe a little bit more, formula about like F tensor F, yeah, F tensor G, yeah, this guy. So on the right-hand side, you want to construct von Neumann algebras, right? On the right-hand side, you want to construct tensors of, or just infinite dimensional C-star algebras. But the tensor product here is done through some kind of universal construction.
Yeah. So algebraically, everything is fine.
Yeah.
Right. If you use the algebraic tensor product, you can sort of just.
Yeah, but that's the thing. I can't think about like the Heisenberg algebra, right, which admits no finite dimensional representations. So there are no non-trivial finite dimensional modules for this guy. So like if I don't extend this deleting product in some sense to like non-semi-simple categories or functor splitting categories, then
the Deligne product. I mean, you've activated my trap card because I always have my copy of tensor categories on me. But the Deligne product is not right. Like it just needs a k-linear abelian category that I guess has to be locally finite. So that might trip you up. But the reason that it has to be locally finite is so that you get a formula about how the Hom spaces work, which if you didn't want finite dimensional things in the first place might be okay. I will not make a stronger statement than that. But definitely like the abelianness, I don't think you can. That's also going to make.
Right. Locally finite is a statement about the Hom spaces on every simple, right? Between every simple.
Yeah, if you like, I mean, it's about all the Hom spaces, but it's enough to check on simples. The thing with the locally finite is you right, like the Deligne tensor product has formulas like this. So Hom x1 y1. I'm not writing the tensor symbol. X2 y2 is isomorphic to Hom x1 x2 tensor. Y1, y2, there's only one thing I can write there, right? That's sort of the idea. Okay. I need to go somewhat abruptly because TiVo is talking as of 20 minutes ago, and I'm fine skipping the introduction part, but I do want to know why there's not that many V2 categories emitting a fiber functor. That's what he's talking about today.
Oh,
thank you for speaking, David.
Yeah.
Thank you.
Thank you.
Bye, everybody.